กดไลค์
ออนไลน์
Where do you see anything like that? The yellow shape.
China people.
Flick Candy Crush.
Okay, so today we're on tutorial 6, and in this tutorial the first question is on instruction level parallelism, and then the other two questions are on virtual memory. So let's go on to question number 1.
This lecture was before recess week.
Yeah. The Jason
Is it attended?
took Thomas away.
Okay, so
Kita sayang.
Gaussian elimination.
question number 1 gives you some code fragment. So this code fragment is part of the Gaussian elimination algorithm, which can be used to solve linear equations. Okay, so in this algorithm, we try to solve linear equations by taking one row of the matrix and adding together another row of the matrix multiplied by some constant. So here we load xi and multiply it by a constant a, and then we add a times xi to yi, and we do this for the complete row of the matrix, and that can then help us to solve this linear equation. Okay, so this is just part of the algorithm for solving linear equations. So here we have a loop. Load xi, multiply by a, load yi, add a times xi plus yi, store back in yi, decrement the x index, decrement the y index, and then we have a loop. And we can assume that the row of the matrix, or the vector, is of length 100, and initially the register R1 has the value of 800, and F2 contains the constant A. So we're asked to execute this algorithm using an algorithm or a design presented by Tomasulo. So this architecture, this is a hardware algorithm for executing instructions out of order. The idea here is that we can have a set of different functional units. So we may have some floating point adders, we may have some floating point multipliers, and the instructions of the code don't have to be executed strictly in order. They can be executed out of order. So we can be executing a multiply operation at the same time as we're executing an add operation, and so on. So I think you've considered this architecture in the lectures, so I won't go into the details, but what we're asked to do is to go through the code and work out how many clock cycles it will take to execute that code fragment on this architecture. Okay, so we have some assumptions. So we're going to assume that the branch, we predict the branch as being taken. So for the different iterations of the loop, that will be the correct prediction. We also assume there's no forwarding between function units except on the common data bus. Okay, so to go back to the architecture, we have a common data bus which is used to write back the results. So if we have a multiply operation, then the common data bus can write back to the results either to the FP registers, or they can be written to these buffers. Okay, so we have a common data bus for writing back the results. We also assume that the branch instruction is executed in the integer function unit. And then these different function units take a different number of clock cycles to execute. So we assume that the integer function unit takes 1 clock cycle. We assume that the floating point addition takes 2 clock cycles. The floating point multiply takes 5 clock cycles. And a load and store operation takes 1 clock cycle. And for this example, we're going to assume that we have just one functional unit for each of these, but we have a number of reservation stations. So the reservation stations are used, the instructions which require this function unit, we can put the instruction in the reservation station, and then that reservation station, it will wait until the values are ready to be executed. Okay, so this hardware design detects the data dependencies automatically. So if there's a read after write dependency, it will detect when the value is ready to be used, and it will wait accordingly. So the instruction is put in the reservation station until it can be executed by the function unit. Okay, so are you clear on the architecture? Any questions about the architecture before we go into the example? Okay? Okay, so let's go to the code then. So we're asked to calculate how many clock cycles it will take to execute the whole code sequence. So to do this, we fill in this table. The question gives us the first 2 entries in the table. So we start off by loading the first value of the vector into the register F0. So that instruction is issued in clock cycle 1. It can be executed in clock cycle 2, and the load and store takes 1 clock cycle, so we can write back in clock cycle 3. After loading the value into F0, we want to multiply the value in F0 by the constant A, which is in F2. So that instruction is issued in clock cycle 2. We can't execute it immediately because we have to wait for the value to be loaded into F0. And that value is only written back in clock cycle 3. So we can't start to execute until clock cycle 4. And the multiply takes 5 clock cycles, so we can write back in clock cycle 9. Okay, so we're given those. We need to fill in the complete table. Okay, so let's go through this table in detail.
Very easy one.
So,
Just leave blank.
okay, so I've already talked about the first dependency. We have to wait for F0 to become available before we can execute the multiply. In clock cycle 3, we can issue the load for the second vector, so we can load that into F4. So we issue that in clock cycle 3, we execute it in clock cycle 4, and we can write back to the register in clock cycle 5. Then we want to add those two values together, but again, here we have a data dependency. So the instruction is issued in clock cycle 4, but we can't execute it until the value of F0 becomes available. So it's written back in clock cycle 9, so we can execute it in clock cycle 10. And then the integer, the add instruction, we're told, requires 2 clock cycles, so the add will be executed in 10 and 11, we can write back in 12. Okay, and then we store that value of F0 in the memory location, but again, we have to wait for the value to become available.
Step by step.
So this value
That's quite long.
is only calculated, is only written back in clock cycle 12, so therefore we can't execute the store until clock cycle 13. Okay, so we write back the value of F0 to the address given by R2. After that, we want to subtract the X index and the Y index. So the first subtract, we can issue the instruction in clock cycle 6, execute in 7, write back in 8. The second subtract instruction, we can issue in 7, execute in 8, but then we have a problem, because we can't write back in clock cycle 9, because if you look closely, this multiply instruction is already writing back in clock cycle 9. Okay, so this multiply instruction is using the common data bus. And we can't write back the two values at the same time, so because the common data bus is used in clock cycle 9 by the multiply, we have to wait until clock cycle 10 before we can write back the result of this subtract. Okay, is that clear? We only have one common data bus, so for any given instruction, we can only write back one instruction at a time, and we're already using the common data bus for the multiply. Okay, so far? Okay, and then we have the branch if not equal to 0. So again, we're told that the branch instruction uses the integer function unit. And we have an integer subtract here for R2. Because we have to wait for the common data bus, the integer subtract is still in the execute cycle in cycle number 9. Okay? So therefore we can't execute the branch instruction until the integer function unit becomes available, which is in clock cycle 10. Okay? So we have to wait for the integer function unit. Okay, and then we go on to the second iteration of the loop. So the second iteration of the loop, we issue the instruction to load in clock cycle 9, we can execute in 10, write back in 11. The multiply, we can issue in 10, but again, now we have to wait for F0. So F0, we don't write back until clock cycle 11 for F0, so therefore we have to wait to clock cycle 12 to execute the multiply. And then the multiply takes 5 clock cycles, so we can write back in 17.
the 方法 is also
Sorry?
the
the fourth row, right?
Fourth row, yes.
Yeah, we are also waiting for F0. That's why fifth row only started at clock cycle 13. But how come for the next one it can straight away start at clock cycle 12? We are still waiting for
Sorry, say again.
on the fourth row,
This one.
the write back for F0 is only done at clock cycle 12. That's
Yes.
why for the fifth row, the execution only starts at clock cycle 13.
Yes.
So at the bottom, right, how come the multiply can execute at clock cycle 12?
Okay. Good question. Good question. So the reason is that this is a different value of F0, because this is the value of F0 in the second iteration, this is the value of F0 in the first iteration. And the hardware can do renaming, so the hardware can detect that this is a different value of F0. So there's no data dependency, because this value of F0 comes from the first iteration, this value of F0 comes from the second iteration of the loop. And the hardware can detect, with this algorithm and this design, the hardware can detect that it's a different value of F0, and that there's no data dependency. Okay? But very good point, very good point. So the hardware includes renaming for different instances of the same value. Okay, so again, we can start multiplying clock cycle 12, finish in 17, and then the load from the second vector, we can issue the instruction in 11, execute in 12, write back in 13. Then we can add the two values together. Again, we have a dependency. So this value of F0 is written back in 17, so we have to wait to 18 before we can execute. The add takes 2 clock cycles, so we can write back in 20. Then we have the store. Again, we have to wait for the value to become available. So the instruction is issued in clock cycle 13, but we have to wait until clock cycle 21 before we can write it to memory. And then we have the subtract. So first subtract issued in clock cycle 14, executed in 15, write back in 16. The second subtract issued in 15, execute in 16. But again, we have the problem that we cannot write back in 17 because, again, this multiply operation is writing its result back in clock cycle 17, so the data bus is not available. Okay, so we have to wait until the data bus is available and write back in 18. Okay, similar to this situation here. And then the branch instruction again, we can issue the instruction in 16. Again, the integer function unit is occupied in clock cycles 16 and 17, so we have to wait until clock cycle 18 before we can execute the branch. Okay, so this example illustrates how you can execute instructions out of order if there are no data dependencies. So, I mean, you can see that this add operation here is executed in clock cycle 18, but the subtract is executed in clock cycle 15 before the add. So the hardware detects the data dependencies and makes sure that all of the data dependencies are taken care of, but provided there are no data dependencies, then you can execute the instructions out of order. Okay, any questions on this example? So how many clock cycles does it take altogether to execute the... These two iterations of the loop, how many clock cycles? 21. Okay, because the last instruction to execute is this store instruction, which is executed in clock cycle 21. So in the execution time, if you take the average over the two iterations, we have 21 cycles altogether, divided by two iterations, so it's an average of 10.5 cycles per iteration.
No trust, we trust in that.
Sci life and Ethereum.
Okay, any questions on this example?
Two iteration, type of iteration.
Exam how?
1 hour.
Let's try
So-
anyhow.
The issue one confirm full mark.
1, 2, 3,
So,
4,
to
5,
fill in this sort of table, you need to take into account the data dependencies, because the data dependencies will
Iteration
cause a
also can,
weight.
iteration.
You also need to take into account
column
whether the function is busy.
Instruction also
Okay,
can, lazy
so
for
you
instruction.
have to wait for data dependencies, you have to wait if the function unit is busy, and you have to wait if the common data bus is busy.
wrong.
Okay, so you have to take all of these into consideration.
The rest,
Steady.
Okay, you happy? Any questions? Okay, so go on to the next part.
we need to do again.
So
Do again.
for this part, we have a slightly different assumption.
Put issue. Put
So here we assume that we can issue 2 instructions per clock cycle. Okay, so if we can issue 2 instructions per clock cycle, how will the table change? What will the execution time be? And then also there's a question now with how we can further improve the performance.
names, yeah.
Show that.
Then you will say again. Yeah.
I see now 1, 2, 2, 3, 3, 4, 4, 5.
Oh yeah. This one.
So we have another table here, but in this case you can see that we're issuing 2 instructions in each clock cycle. So the question is, how many clock cycles do we need altogether? So again, let's go through this in detail.
19.
In clock cycle 1, we can issue instruction 1, so issue the load instruction, executed in clock cycle 2, right back in clock cycle 3. We can also issue the multiply instruction in clock cycle 1, but again, we have a data dependency, so we can't execute it straight away. We have to wait for the load instruction to write back, and then we can execute the multiply in clock cycle 4. The multiply takes 5 clock cycles, so we write back
How to
in
know
9.
sir? Multiply 5 clock cycle.
In clock cycle 2, we can issue the load, execute in 3, write back in 4. And we can also issue the add in clock cycle 2, but again we have to wait for the value to become available. Okay, so we
Multiply you take 5 clock cycle.
write back F0
Standard one or
in
what?
clock cycle 9,
Yeah.
so we have to wait until clock cycle 10 to perform the add. And then the add takes 2 clock cycles, so we write back in 12. The store we can issue in clock cycle 3. Again, we have to wait for the value. Okay, so the value of F0 we write back in 12, so we execute in 13. Also in clock cycle 3, we can issue the subtract. We can execute in clock cycle 4, right back in 5. And then the second subtract, we can issue in clock cycle 4, execute in 5, we can write back in 6. So here we have a difference from the first example. Remember in the first example, we couldn't write back straight away because the data bus, the common data bus was busy.
Not to,
But here, because we're issuing 2 instructions per clock cycle, if you look, nobody's using the data bus in clock cycle 6, so this subtract can write back the value in clock cycle 6.
As in the second iteration, right, you say that wait for integer unit, that's why the execution part goes from 8 to 10. Now come for the first iteration, can go straight from 4 to 5. Then go to
Sorry, say again.
for the 6 and 7th row.
6?
Clock cycle 4 and 5 for execution.
Yes.
Execution. Yeah, so we are waiting for the integer unit, right? So subtraction will take 2 clock cycles. I thought we have to wait until clock cycle 6.
No. Floating point addition and subtraction takes two clock cycles. Integer function unit is just 1 clock cycle.
Floating point. How to know floating point? Where? Where's the floating point?
Okay. If you look at this screen,
But how come the second iteration have to wait for
this one here.
all the way down? Clock cycle 8 and 10 first. All the way down. Second iteration.
Okay, let me get on that.
Yelah, you
Okay.
go back. Never even read that part.
Okay, so I mean, if you look at the assumptions, the integer function unit just takes 1 clock cycle. So an integer subtract is just 1 clock cycle. Okay. So here, okay, the first subtract, issue 3, execute 4, write back 5. Second subtract, issue 4, execute 5, write back 6. Here, the branch instruction, we issue in clock cycle 4, but the integer function unit is being used by the subtract in clock cycle 5, so we can't execute in clock cycle 5, we have to wait until clock cycle 6. Okay? And then going on to the second iteration, the load, we can issue in clock cycle 5, execute in 6, write back in 7. Issue the multiply in clock cycle for 5. We have to wait for, okay,
No. Eh? Eh?
okay,
I never read.
the wait for this, the right back of the first.
Why?
so we're assuming we only have
we have to
one
finish that one
we only have one floating point multiply unit. So if you look carefully, we're already executing a multiply instruction, and the multiply instruction does not write back until clock cycle 9. So
One is also F0.
here we have to wait for the
Keep track all the way on.
multiply unit.
You see the load F0 also can use what cannot make? The first iteration number 2.
So we can execute,
5, 6,
execute this in
7.
clock cycle 10,
Okay, one can
right back in
go.
15.
Then why the execute must wait until number 10? Why not 8?
No, because because
Multiplier still working on top.
yeah, the second one up to 9.
And
That's
then
why
the load instruction,
yeah.
the load instruction we issue in clock cycle 6, execute in 7, right back in 8. The add, we have to wait for the value of F0 to become available. So we
exam just
execute in clock cycle 16 and write back in 18. And then the store, again, have to wait for the value to become available.
No, you see.
So we can store the value in clock cycle 19. Here we want to do a subtract. So we issue the instruction in 7, execute in 8. But now, if you look carefully, we
Number 9.
are using the common data bus in clock cycle 9. So we can't write back in clock cycle 9. We have to wait until clock cycle 10 to write back.
Okay, okay. Go for one.
And then this instruction here, again, we have to wait for the integer unit to become available, so we can execute in 10, write back in 11. And then the branch instruction,
Okay.
we actually have 2 reasons for waiting here.
Okay.
So, first of all, we have to wait for the value of R1 to become available, and also the integer unit as well. It's not available until clock cycle 11. Okay, does that answer your question? Okay, good. Okay.
Still have to do very slowly. Sure, easy can or something.
Okay, so
Can but you must do very slowly. Waste time.
We need to wait for F0 and the
I think this
floating
one will
point
come
unit,
out.
floating point multiplication unit. We only start the execution clock cycle, one clock cycle after the write back. But how come for integer unit, I can just start at the same clock cycle?
UI means integer.
Yeah. Yeah, even ninja.
UI means integer. The multiplier, yeah, we know.
The second
No,
last
this is
row
not
and
not
the
adding,
third
this
last
is actually
Yes.
decrementing the index.
So
So
you
it's not
see the
considered
comment says
that
that
as
we are waiting
subtract.
for the integer unit. So
Yes.
the write back for
Consider that
integer
as
unit
integer
is clock
unit.
cycle 10, right?
yes.
Then we
So it's
execute at
just
clock
an
cycle
integer
10. How come there's no need to wait for one
think so.
clock cycle? Execute at the
You
next
see
clock
the,
cycle.
your second last one, you save it for integer
Whereas
unit.
for F0
I
and
guess that's an
floating
integer.
point multiplication, we waited for one clock cycle.
I think you need to go out there and show.
The whole UI change.
What do you mean?
So
Oh, I mean the user interface changed.
you mean in the game, in-game?
Yeah, when you log in, right, when you go to the menu, right, change already.
Oh,
You can think the right info change. Like so far,
cinematic night.
the
Even more high than
Kerrigan is more human than very human. But she still can control the zero.
Okay,
First
so
campaign is
fine.
just the first 2 campaigns are very simple.
She haven't
Yeah, I think you made a mistake here.
she still know what she's doing.
Just human really.
Got mistake,
Then
got mistake,
the
got mistake.
second campaign spoiled. The second campaign is you use a human form of yourself. But I'll leave it to you to play around with the character. But not bad.
Edition D is
The achievements are quite interesting also. The first one,
You play what difficulty? Hard. I'll play the there's 1, 2, 3, 4, right? I'll play the second one.
no,
the
they say
hard
easy. Like how come
hard
you
can
can
still is not
do
really
clock cycle to
Easy,
wait for
normal,
the integer.
easy.
is it normal hard
Okay,
also?
so
Dia tak bilang mana tak lah.
Betul,
Tak,
betul.
dia cakap get back. Get back.
Sama I just play easy.
Start.
The first can make an achievement that's complete in less than 10 minutes.
How come
Can try.
How come the-
It is a challenge.
8 right? How come the 10 right? They have to wait 2 clock cycle. Oh, supposed to be one only.
So in this case, if we issue two instructions per cycle, we can take the last instruction to execute. So the last instruction to execute is in clock cycle 19. So the time of iteration is 9.5.
That's 2 clock cycle.
Ni betul lah.
So
Normal lah, normal.
how could we further improve the performance? Any suggestions?
At 1000
Sorry?
more.
Add more floating point unit.
You reduce the cycles.
At 1000 instruction issued per clock cycle.
Okay, so I mean there are a few ways.
Issue all
There's a
one
few
time,
ways
you
we
wait
can
for
improve the
everything.
performance.
More functional unit.
More function units, yes. So which, if we have more function units, which function unit should we have more of? In this example, which particular function unit is for? Well, there's a few function units actually, but
Multiply.
the multiply. So yeah, we could have a second multiply.
Multiply take 5 clock cycle what?
Yeah, no. So you take very
We
long.
could have another
wait very
multiply
long.
unit.
But why must you want to add another?
Also,
cycle?
we could have another integer unit because in some cases
So you don't have
we're
to
waiting for the integer unit.
Pipeline,
Or we could pipeline. So
Remember just now
there's a number of
asked
different
why
ways we
then
can
start.
improve the
Oh, that
performance.
one I
Need to
know.
wait for 9
One way of
5
improving the
cycle.
performance is by adding
If you got 2
more.
multiplier,
Okay,
straight
start
away
with,
start. Save 4 clock cycle.
Oh, I see.
Save
Yeah,
what,
yeah,
4
that's true.
clock cycle. 4 or 5 clock cycle.
Instead of one, you have maybe another one more, then you can make it faster.
Okay, so let's go on to the next two questions. So question 2 and question 3 are about virtual memory. So here we assume that we have a computer which has 16 pages of virtual memory address space, but it has only 4 physical pages, only 4 page frames. So initially we assume
only
that
one-
the memory is empty,
One way.
and then we have a program which references the virtual pages in the order 072758924. And we're asked,
Wow, like so long.
OS,
suppose we use the least
LRU.
recently used algorithm for swapping out pages. How many page faults will we have? Or alternatively,
We haven't done.
that one you can.
if we use the first in, first out algorithm, how many page faults will we have? So let's use
Michael
these
to
two
come and teach us.
algorithms for this particular example.
Very easy. I remember in the exam, I cannot go start.
Okay, so
they
we
ask
have
us to-
4
to
physical
go
page
start.
frames. So if the program references
negate.
0727, we can load the first virtual page 0 can be put into the physical page into the page frame. The 7 can be put in. The 2 can be put in. When we access the 7, it's already there, so it doesn't cause a page fault. And then when we access 5, it can be put into the 4th entry of our physical page table. Okay, and then we access 8. So when we access virtual page 8, we have this least recently used algorithm. So the virtual page that was least recently used is 0, so we replace 0 by virtual page 8. Then we try to load 9,
Remove 7.
How you get the 5 to 7?
and again, using the least recently used algorithm. 7 was used more recently than 2, so 2 is the least recently used, so we replace 2 by virtual page 9. Then we need to reference 2 again. So in this case,
Oh, yeah.
the least recently used page is 7, so we replace 7 by 2.
If me, I'll arrange in order.
No, the last semester
Whenever
one
I use,
easier.
I'll put it on top. And when you
The table used the last year, the last
And then
semester easier, the
finally,
OS one.
we
one
reference
confusing, eh?
virtual page 4, and in this case 5 is the least recently used, so we replace 5 by 4.
How you get?
So how many page faults do we have altogether?
How you get the first one? 5 to 7, no? Got given.
Yes.
7.
How many
First they
page
put
faults?
0, then put 7,
Okay,
then
so
put 2. But
the
7
first
is
4
already
pages,
inside
the
the
first,
what so
No, but how the starting you get 0, 7 to 5?
filling up the
In this order?
page frame it initially
first
causes
0,
page
then
faults.
second one 7.
So we have a page fault
third
on
one,
0, we have a
And
page
fourth
fault
one
on
is 7 because
7,
it's already there.
page fault
So
on 2.
I ignore that, then I go to 5.
This 7 is already there, so there's no page fault. Page fault on 5, 8, 9, 2 and 4. So we have 8 page faults altogether. Okay, what about the first in, first out algorithm? So again, we start off in a similar way. We reference page 0, page 7, page 2, and then 7 is already there, and then we reference 5.
First in, first out.
Then we reference 8. So again, using the first in, first out algorithm, the first page to be loaded was 0, so we replace 0 by 8.
Place 7,
But then, when we come to reference 9,
place 7
which page do we replace with 9?
7.
Which one?
9 page 4.
7. Okay, so
Then
here we
but
have a
the code has
difference,
no page fault.
because using the first in, first out algorithm,
And
7
4
was
page with
the
2.
first one to be loaded, so we
Ah, two ah,
replace
three ah.
7 by 9.
4 with 2 ah. 4 with... 4 with...
And then when we reference 2 again now, in this case, when we reference 2 is already there.
Yeah.
So this 2 does not cause a page fault.
Yep.
And then we reference page
4
4.
with 2 ah.
2.
Which page do we replace by page 4?
2.
2. Okay.
This is lesser page.
So how many page
7.
faults do we have here?
7.
Okay, 7 altogether, because in this case, the 0, 7, and 2 cause a page fault, 7 doesn't, 5 causes a page fault, 8, 9, 2 doesn't, and 4 causes a page fault. Okay, any questions?
Apa ni makan dulu lah. Makan dulu.
This one is the easiest.
Lepas ni kau dah tak ada kelas apa-apa kan? Nak pergi kan?
Pray the exam come out this one.
Kau nak belajar kan?
Exam come out this one. This kind of question. Simple,
Nak
simple.
belajar kat mana?
Not like
Not like the Somasu or whatever shit. I give
Thomas
Library
Rose.
lah, Livinam.
Thomas Rose. Not sure come out one lah. Confirm one. It's not a long one lah. This not a long one lah. will come out.
Okay, so
4 hours papers lah, question come out.
What is the brand of the tomato? Kraft. Kraft. Maggie ah, Maggie. Kraft is Maggie. The tomato sauce also Kraft ah.
Why put question 3 inside? Oh, yeah.
Give me the highest one.
Just say I come from tomorrow.
Why?
Okay, send me.
When you start? Oh, tomorrow come out.
Yeah, man. Football.
Honestly, they always look for Taeyeon.
Taufik never go IT show.
Never.
Okay, so let's go on to question number 3 then. So again, we have a question on virtual memory. We assume that the page size is 1024 bytes. We assume that we have 8 virtual pages and 4 physical pages in the page frame, and we are given the page table.
Why different?
So in this page table, virtual page 0 is in physical page 3. Virtual page 1 is in physical page 1. 2 is not in memory. 3 is not in memory. 4 is physical page 2. 5 is not in memory. 6 is physical page 0. And 7 is not in memory. So what addresses would cause page faults? 2,
1004,
2, 3, 5, and 7. Okay, so any address in page 2, in virtual page 2, virtual page 3, virtual page 5, or virtual page 7 will cause a page fault.
Once we address one, so you must score times 1024.
So if you work out
Oh, this I remember.
what these addresses are, given that the size is 1024,
How come?
okay, so virtual page 2 is not in memory, and virtual page 3 is not in memory. So anything between 2 times 1024, which is address 2048, and 3 times 1024 plus 1023,
okay.
which is 4095, will cause a fault. Virtual page 5 is not in memory, so anything between 5120, which is 5 times 1024, to 5 times 1024 plus 1023 will cause a fault. And similarly, page 7 is not in main memory, so anything between 7168, which is 7 times 1024,
Once you
to
want to
7
find
times
the range of the
1024 plus
address,
1023 will cause.
495 is the last number. So you must 3 times 1024 plus 1023.
And then we're
The
asked,
last address one.
if we're given some virtual addresses, 0, 3728, and so on, what are the physical addresses? Okay, so the way we do this is that first of all we have to work out what the virtual page number is. Then we map the virtual page to the physical page according to the page table, and then we add any offset. So what is the physical address for 0? Okay, if you look at the table on the other screen, you see that 0 is mapped to page 3. So what will be the physical address for 0?
What is
3
0?
3 times 1024.
Yeah, 3 times.
Then the 3 0 really.
Okay. So
3 times
in this case the offset is 0, but physical page 0 is mapped to virtual page 0 is mapped to physical page 3, so the physical page is 3 times 1024. Okay, 3728 is not in main memory because virtual page 3 we know is not in main memory, so 3728 will cause a page fault, so it has no physical address. What about 1023? What will that be mapped to? What's the physical address for 1023?
10.
Okay?
1023.
3 times.
page frame 3, you must calculate the offset as well.
3 times 102
Okay,
plus
so 1023 again is in page 0. So page 0 is mapped to physical page 3. Here we have an offset of 1023. So 1023 will be mapped to 4095.
Then 1024 is
What about 1024?
1.
What would that be mapped to?
1 times 1024 plus 1024.
Next page.
Yes, what?
First.
1024. Okay, if you look at the table, virtual page 1 is mapped
Frame page 1.
to physical page 1. So in fact, in this case, the physical page address is the same as the virtual page address, because it's the virtual page 1 is mapped to physical page 1. 4096. What would that be mapped to?
Page
4.
Somebody tell me?
204.
Okay, so virtual page 4 is mapped to physical page 2. So 4096 is mapped to 2048. And then the last one, 7800, is not in the main memory, so that will cause a page fault.
is 3 times 102.
How do you know, Why 4096 went to 2048?
Okay, any questions on that?
2048.
Macam mana belum name Kenneth, teach me how to make.
Which one?
0, the first one lah.
0. First one is
They ask for 0, right?
0, right? Virtual 0, right? So virtual 0 is where?
Page frame is 3.
Virtual page 0 is here, right? So it's the very first address here, right? And page frame 3, right?
So, I mean, there are a number of ways we improve
In
this.
frame 1
So here
is
we're waiting for
1024, but in frame 3 is 1024 times 3. So that's times 3. Then that is 307. Then the second one is what?
1023.
That got an error. The second one is 1023, right?
Where?
The second one is 1023, right?
3728, where got error?
Error, because
Not in memory,
it's not in memory, right? Yeah, so next one is 1023, right? 1023 is the last address in this one.
Yeah,
It's the last address in page 0. Because 1024 you go to page 1 already. Yeah, so just now you know what is the starting address of page 3, right? So you take 1024 times 3, then you need to plus 1023, the offset, to get the last page of this frame. That's why it's 3 times 1024 plus 1023.
Hold on,
Something like that. You need to know the starting address for the page, then you add the offset.
See your baby. But the 3728, how you know it's page 4?
Because 3728 is in which page? 1000, 2000, 37, 1000, 2000, 3000, right? So it's page 1, page 2, frame 3, right? 3. So you look at virtual address. Where's my paper? Here. You look at virtual address 3. 3. Find the memory.
Oh, so then go attendance, anything.